Okay. So I'll just share that screen. So yeah, I'll just run through these notes that are in here. So this was chapter 9, functionals. So the learning objectives for this one were to define functionals and use, basically, mostly it's looking at the functions in the per package. So there's firstly the set of map functions, and there's walk, reduce, and accumulate, and then a couple of other ones for dealing with failure. So firstly, there was kind of defining what are functionals, which are functions that take a function as input and return a vector as output. Which I think was partly where it's kind of, I was trying to get my head around the fact that then, or some of them, they say they take a vector as input, but that could also be an entire data frame, because that can be a list of vectors of the same size. So there can be kind of different inputs. That and then it's just kind of mentions the base R kind of equivalents that I have definitely used for, but don't particularly tend to use them very much now. And so they're an alternative to loops, and like we kind of said in the looping, or whatever that chapter was where we covered loops, functional is kind of even better than a for loop, which is better than while, which was better than repeat. And kind of, so one of the reasons for using it was to make the code a bit more straightforward, and to not have big long loops that maybe the logic gets a little bit messy. So the first family of functions was the map. So from the per package is map variants. So this was where it says, so it takes the two arguments. So we've got a vector and a function. And so this picture is from an example a few kind of later down in the book. So I think that the first one in the book, it doesn't have this blue square here, because that's to just illustrate that if you pass extra arguments, then these kind of propagate through each time. So you don't have to have that one. You can just have map, pass it a vector and a function, and then that function kind of gets applied to each of the elements in the vector. Then this example is just supposed to be sort of what goes on behind the scenes, but that's clearly not the exact code, which I think is written in C++ or something. So per map is kind of very similar to the base function L apply. So we get a list back from the map function. So it's quite general. It's quite bit. We can obviously get anything back in any size because we've got a list. And yeah, okay. So the length of the input is the same as the length of the output, but depending on what we're doing to it, I guess depends on what we've got in those lists. There are then associated functions that then return atomic vectors rather than lists. So we've got the map kind of character, double integer, and logical, of which there are various examples of using in the book. So they use the empty cars example in the book, the kind of run type of, or is doubles, which then goes through those different columns and kind of collapses the result down to an atomic vector. So there's another example here. So this is just a function that multiplies by 3. So we're taking the values 1 to 3 and then tripling them. Then the map function returns a list always, but if we might not want that, so we could use map double, and then that will return a vector, an atomic vector. And then this is just using map logical to get a logical vector back up. Then there's some examples of anonymous functions. So sometimes we want to apply a function that might not be defined elsewhere, although here it's just using the mean function, but we can define that function within the call to map, and there's a couple of different ways of kind of syntax for writing these anonymous functions. So this first one, we're just saying function X, and so then we're defining that function afterwards, which is kind of how they used to write things for lapply. But then there are some kind of short cut ways to do this now with the Perl function, per functions. So you can use the twiddle to set a formula. So instead of saying f equals function x, we can just use the twiddle and then define that function, and the dot x is going to refer to the input data, and just apply that function to every element of that. And yeah, so we can simplify it even further. So without having to have these brackets on here, we can just say what our x is, what our function is, and then if there are any further arguments to pass to that, then they can just be added on. So I think these ones seem kind of reasonably simple. I think it's when things start getting more nested that they get a bit more complicated, at least in my head. The modify function is a little bit different in that the output is kind of the same structure as the input. So we're not just using map and then always getting back a list. So in this case, well, there's an example where map is being used. So we've got a simple data frame with 2 columns, where the first column is 1 to 3 and the second, the numbers 6 to 4 in it. And if we use map on that and just multiplied each of those values by 3, then because we use map, we would get a list returned. But maybe we don't want that and we just want to kind of modify in place, then the modify function is kind of what we might be after there. Then we've got some examples about per style. So I think the idea for this bit is, so in the book it says, before we go on to explore more map variants, we'll just have a look at kind of using them to solve a realistic problem and kind of stepping through thing there. So it's not quite the example from the book, but it's taking that empty cars data set and extracting the first 20 values from each column, and then piping that to the map double function to get the mean. So then we've got atomic vector out of that, and then we're just running ahead to get the first 6 there. And we've got another example, which I haven't actually looked through. There's a bit more going on this code, which I guess we could try and run. See, so I don't have the Tidy Tuesday package, so that's not going to work. Actually, I guess I could install that. But I think this, though, there are some other examples in the book as well. Just kind of stepping through and applying the functions kind of multiple times. Then kind of goes through the different variants. So I quite like this table because it kind of summarizes quite a few of the different variants from the per package. So we've got kind of however many arguments on the rows. So either kind of 1, 2, or if we do want the index, because sometimes we want to kind of step through by index, and then there's kind of the n arguments, and then what our inputs are. So I think this is quite nice as a reference table. Then we've got so yeah, I guess we've kind of already seen these atomic, or no, sorry, these aren't the inputs, aren't they? They're what is returned. So we've seen map that returns a list. We've seen the map logical, which returns atomic, along with the map double, etc. What we haven't really seen are taking in 2 arguments and kind of iteratively going through both of those at the same time. So for that, it's map 2 and associated functions. So we've got an example here where using, this is just map double. So we've already seen that for where we just have one input or one set of inputs. So the input is x, which is 1 to 5, and then the function, we're just raising that to the power of 2. So you get this result. And then this is the map 2 equivalent. So it will return the double, because that's the syntax of these. We've got the underscore and then what it returns. So for our inputs, we've got x. So the first set of inputs is 1 to 5, and then the second one is 2 to 6. And then it will step through each of those. So for our result, first one's going to be 1 to the power of 2. And then the second one is going to be 2 to the power of 3. 3 to the power of 4, etc. So I think that's quite a nice, simple example for that one. Then we've got some notes for the benefits of using map over the apply family. So I think there's quite a few improvements. It's a bit more, well, it's a lot more consistent with syntax and the way that it returns the objects, whereas, yeah, so we always know the return values, whereas the apply ones kind of coerce into different types of outputs. Sometimes they try to simplify things, so and sometimes not. And it's nice and fast, and we can pass in additional arguments. So we haven't looked at the walk function yet. So this one is for when we are not returning a list or a thing. So we're just using that for its side effect. So like generating plots or writing out files or saving objects. So we're just iterating through a vector again, and then we've got some function in there that we're just using for the side effect. And we don't get anything returned from this. So I guess, yeah, in this case, there's just an example of writing out the numbers 1 to 3. And so it will write them out, but then we also get this object returned that isn't of much use. So we don't really want to use map there. We might as well just use walk, which just walks through them and doesn't return anything. Oh, and we've got p-walk. I haven't actually seen that one. Is that one in the book and I just missed it, or is that one somebody else's added in? Oh no, it is there. Okay, so for n arguments not returning anything, then we've got p-walk. Okay, so I guess so this one is iterating through so going through empty cars, it's splitting up by that factor and then creating a load of plots. So just run that. I just end up saving. Take a while. So that goes through each of these parts. So it's creating 3 files. So we've got 3 plots here. 1, 2, 3, and then 3 parts. And it's just using p-walk to go through those. So passing it a list of the parts and the plots. So this must accept the arguments .l and .f. So the function is ggsave, and then it's just got a temp directory for the path. And I guess we could use walk 2 if we just wanted, if we just had 2 paths and plots. And so walk 2 and p-walk all invisibly return .x, the first argument. Okay, so you can put them in pipelines and it will still work. Okay, so IMAP is then for if we are iterating through the kind of data and the index. So yeah, so it's a bit like map 2 in that you're iterating through two things at the same time, but the second one is derived from the names. So you're going through those indexes if it's named, or just those indexes if not. These two produce the same result. We've only got one thing there, haven't we? Maybe that is something to add. So here we're using IMAP character. So the inputs, the empty cars data set, and then the function is just pasting together some text, and we've got it's also running this function. So we're taking the mean and rounding that. So we've got X as the input, as the data, and then Y in this case is the names of X. So it constructs this string here. So the name has a mean of. So that's an example of IMAP. And then PMAP. So PMAP is going to be for n arguments again, and we get a list back. So we can pass in a named list or data frame. So let's have a look at this example. So we've got a set of parameters. That's this tibble, n, min, and max, and then we're running PMAP and passing in this tibble, and then the function is looks like runner. So selecting from the uniform distribution. So these are going to be the number of values that we want, and the minimum and the maximum value. So for PMAP, you can pass in a named list or a data frame as arguments to a function. Okay, so those are just the arguments that are, I don't know how you pronounce it, we call it runif or R unif. So that takes in the arguments n, min, and max. So then PMAP just kind of walks through each of these rows in the data frame, well, in the tibble. And yes, so this then produces the same result. So you could have it, so we could have, params list. Which contains the same values, but then that was getting piped to PMAP, which should then do the same thing. It's going to get really do params list. Then we get the same kind of result, but it is randomly sampling, so we don't get exactly the same numbers there, but it does work in the same way. I think the tibble looks a little bit neater. Maybe kind of iterating through those. But either way works there. Then we have got the reduce family. Which I have not used before. So this looks like it would make complete sense to use if you have the need, and I'm sure it is super helpful if you need that. I'm not sure I've come across an occasion where, probably have at some point, but wasn't aware of it. So this kind of, so it takes a vector as the first argument, then a function, then the dot init initial that is optional, and then it applies this function repeatedly to the lists, kind of reducing it each time, so that eventually there's just a single element left. So I think there are some examples of this. So these examples are different to the ones in the book. I think this one's probably simpler. So this is just showing that if you add up 1 + 2 + 3 + 4 + 5, we get 15, which is the same as running. Why we need the seed for that? Is that because we don't have anything random going on, right? So I don't know why it's setting the seed. Maybe it's this. So if we run reduce on 1 to 5, and the function that we're using is the plus, then it's going to go through and do 1 + 2, then we get that single answer, which is a 3. Then it's going to do 3 + 4, or 3 + 3, and just kind of condense them each time. And then there's that optional initial argument. So this is testing whether these two are identical. So adding up those 6 numbers, including the 0.5, and that's the same as using the reduce function from 1 to 5 with the plus as the function and setting that initial value. So maybe that's why we're setting the seed, to check whether that's identical with the floats. So in the book, then it also talks about accumulate, which I also had not used before. I don't know if that's in here. So I've got another example of, oh yeah, there is accumulate down there, of reduce. So using a plot of MT cars, so we've got plotting out the HP versus MPG. So I guess that's just adding the different points on, which are slightly different sizes, although it's not particularly, oh right, yeah, so they're just plotted on top of each other with the smaller point size. So then if we use the reduce function, going from 8, 4, and 2, then we're passing into that. Then we're adding, doing G on point, and the initial value is are those ones here. I'm not entirely sure what that achieves. Yeah, okay. So this is just a different way of adding those on top of each other. So with reduce, we're passing in a vector of values. We've got the function is G on point. Size is Y, so it's going to be those when they're added together and reduced. And then it's got the initial value that you start from. So I guess it's just adding each of those up. Yeah.
So the 8, 4, and 2, the vector of numbers is used for the size of the points.
Sorry.
Yeah, that vector there.
Yeah.
The size is .y.
Yeah. So that's Y that it's going through, and then but yeah. So X is then this initial value, right? That's so oh no, reduce. Oh, I don't know. I think it seemed to kind of make sense with the nice simple version, and then that. So reduce that, and then I guess, yeah, so this is all the function.
Yeah, but how does so there is no, okay, there is the function, there is like this tilde, the formula sign, and then dot x plus G on point. So that plus is used to connect with the initial part of the plot. So that
yeah, so the
otherwise,
yeah, so I guess it's kind of, this is the initial value, so then that's the x. I think maybe there are some easier ways to think about that. There's another example here. Let's look at that one. So we've got a data frame of, so we've got a list called DF that's got age and sex. So age has just got John, who's 30, and then we've got John and Mary, and this is then using reduce, the function is doing a join, a full join on them, which just puts them together. Okay. Yeah, I'm not sure. I think that's just making me more confused about reduce. Actually, so I think
What are these joining to?
the join, so the join is just joining these two data frames.
Okay.
So I guess that would just be the same as doing full join of DF1 and DF2. Right. So that's gonna do the same thing as using reduce for that. So I'm not quite sure why you particularly use reduced in that situation. But maybe would. So I guess there is a function for so kind of reducing and stepping through each of those. I'm not entirely sure when that would be useful, but I'm sure it would become obvious if you had some data that needed that. Because there's a whole set of other functions for it. So there's the multiple inputs for reduce. So there's reduce to, map reduce, that all look like nice and efficient functions if you need to run those on your data. But yeah, I'm kind of unsure as to why you would want to use. I guess maybe this works if you've got lots of them there, and you could just use reduce to join them all together. I suppose we could iteratively go through them. Then we've got, okay, so then we've got an accumulate function, which shows all the steps. So you can actually see what's going on. So this was where we'd used reduce. If we do reduce to add up all those numbers, then we just get the result. But if we run accumulate, then it shows each of those kind of cumulative steps. So the other bits that were, it says not covered. So what we actually got in there. So the book kind of goes through a bit more about output types for reduce, and then also multiple inputs. So maybe should have actually gone through and found some other examples for those. So what we've got in the notes here that are not covered are the map DF variants. So map DFR for row binding and DFC for column binding. Okay, so we've got whole stats. There's a function, yeah. So that's going to take empty cars data set, summarize, take the low number and then create okay, and we get an Rn at the end. So running that over 1 to 2. They are slightly different. Okay, so it's just taking a different number of rows of the data frame. So firstly we've got 10 and then we've got 20, so then we get slightly different summary results there. So I guess the point of this is if you run map on it, then you get the list back. But if you do map DFR, then it just binds it into it binds by row, so you get a data frame back. So is that just okay, so I don't know. Yeah, that's doesn't seem to be in the book. I don't know if there's any particular reason for that. Well, it says life cycle superseded. So so instead it's recommended to use map2 with list rbind and list cbind. Okay, so I guess that's why it's not in the book. So if we just take that output and say list rbind, then we get that same result. Okay. So yeah, should probably update that bit. Okay. So also not covered apparently was pluck. It does mention that in, well, when I've just searched for pluck in the book, I think, but it doesn't say a huge amount about it. It just says the map functions have shortcuts for extracting elements from a vector powered by the pluck function. So you can use a character vector to select elements by name, or an integer vector to select by position, or a list to select by name and position. So there's some examples here where we've got this list of values, and if we just want to pull out so this is the first list, then we can use this syntax. If we run pluck within the map function, then we can extract the first. So in this case, it's just extracting the first element from each list. And then because this is mapped, then it will return the list. If we just wanted that as a vector, then we could use map double, this is using, to extract each of those, the first element from each list, and get that back as a vector. So I think find that quite a useful function. So just have to look up how to use it. Then flatten also is apparently not covered. So yeah, so that's not in the book, which is also superseded. So flatten's been superseded by list flatten. And then there are a whole set of other ones that have been superseded by list underscore C. And then the list R bind and list C bind. So is that list flatten? Okay. So we've got the list. I'm pulling that out. So that's using a map if it's a list, then pluck out the values. And returns a list. And then the other example of actually using, so that's, oh, sorry. So that was the first one that was returned. So we get the list. Then the second example is map it if on the list, if it's a list, then flatten int, which has been superseded by list C, so which combines list elements into a single data structure. So let's just see if that. Okay, yeah, so that just works in place. And then the last example just kind of runs that again. So that's just completely flattening the list. So let's just try that with the new version. So that also works. So then there's a bit about dealing with failures. So safely. So the what's this? I don't know why this isn't, but okay. So I think the next bit in the chapter, because the only bits we've got in here, yeah, it doesn't go through these. So the bits that are in the book then right at the end that aren't in these notes is it talks about the predicate functionals, which I found quite hard to get my head around, having never really properly learned English grammar. Probably the people whose English isn't their first language know more about the grammar. But so this, we've then got the functions some, every, and none. So they kind of, so they're functions that return a single true or false, like is.character, is.null, or all. And we say a predicate matches a vector if it returns true. So these sum, every, and none are kind of similar to using the any, all functions with map logical, but there are some benefits. So they terminate early. So sum would return true when it first sees true. Every and none return false when they first see the true or false. So there are a couple of examples of those. There's also the other function, so is detect and keep. Where we've got a data frame and then it's detecting if anything in that data frame is a factor. And there isn't anything, so it doesn't find it, but I guess you can do detect. The data frame is dot character, and then it finds those. And then similarly, there's the index version of that. There's the keep function, so that it will just keep those in. That's not keeping anything because there aren't any factors in there. But again, I guess if we change that to character, then it will keep those in and then removes other stuff. And then kind of opposite is discard, which again is gonna, well, that one keeps everything because it hasn't found a factor. But if we change that to character, then it's going to discard the characters and keep the integers in this case. So yeah, that was most of those functions. And then the really last bit in the book just goes over some base functionals. So they can get quite mathematical. So I guess, well, there's the apply function. So that's just the base apply for going over. Well, so it can work with two-dimensional data set, but also with more dimensions, which is kind of interesting to try and think about. So there's an example of using apply, but I think generally we can just use the per family unless there are particular mathematical, unless you're working with arrays and things, and doing some, working with more dimensions, then that might be where apply would kind of come into its own. And then there's a few other functions as well for integrate, finding the root, and optimize. But yeah, they kind of have their maths niches. And that then is the end of the chapter. And I think we're right out of time anyway. So that seems like a good time to
you timed it perfectly.
So no, I've lost all the stuff. Okay.